features are of Haskell. Then we're going to table that for now. I'm going to talk about the exam and also the quiz. And then I'm going to, after we do that, I'm going to give you some hints and kind of the approach to use for finishing up the interpreter. So the last sort of stage of the interpreter. So that's the plan. So in terms of what's due today, technically homework 5 and homework 6 are due today. Then homework 7 is being posted, so it's all ready to go. I just don't want to post it because that could confuse people. So so I'll send out a link to the Google Classroom here after class today. Also, I sent a note on, so for homework 5 and 6, as I mentioned, we're being a little bit, or I'm being a little bit looser in terms of when stuff is due. So I would like for you to have 5 and 6 done. If you're not quite done with it, it's fine with me if you take a little bit more time. What I'd like to do is have a mechanism in GitHub or otherwise that would allow people to say, finished with the assignment, please grade. There isn't a great way to do that at this point that I know of. We're working on that. And so if I do come up with something with respect to that, I will let you know. But for now, it's okay with me if you take the rest of the day and even kind of into the weekend, it's fine if you still need to finish up homework 5 and 6. So
tell them that.
I have a question
actually.
Okay. In terms of allowing, letting the grader know, could you create like a simple README file that you could attach in GitHub? You know how normally you could see that right away the moment you open the GitHub and just.
Oh yeah, that's not a bad idea. Yeah, so you could put in a README file that says finished or please grade. The other thing we were thinking about is maybe just doing like a tag or something, using a tag, like a finished tag. That's a little bit more involved. It means it requires more knowledge of Git, I would say. Although I think you can do that through GitHub as well. So that's actually the README. That's a good idea.
Could put it in a commit message.
Yeah, the problem is, okay, so here's what we found and I don't know if it's so much with this class, but the commit messages always basically say finished. Like anytime, the commit messages aren't great. And hey, I'm guilty of that myself. I don't create very good commit messages, but I'm also not trying to be a professional software developer. So, but I think there's some ambiguity with respect to the commit messages. So I don't think it's a bad idea to use commit messages. I just don't know how successful that would be.
Okay, I have a question.
Yes, Jared.
If our GitHub username is not immediately like knowable, like it's not a real name, should we email that to the person grading our stuff? Email our username? Or is there some other way we need to?
Well, so one thing you could do is put your name, make sure your name is in every source code file, and also name the file, the discussion or the write-up file such that your last name is in it, and make sure your name is on that. But yes, I think ensuring that the grader knows who you are is important. And the way I think mainly people have been doing that is, or the Harley's been doing that is through comments and such.
Alrighty.
Mm-hmm. Other questions that people have? Okay, so So then I just wanted to talk about the quiz real quick. So I put a Piazza post about the quiz. So after the class today, the quiz will be available to people. But what's important for the quiz is that it is timed. And once you start it, that's when the clock starts and it won't stop. So you need to begin the quiz only when you can sit down for the full amount of time to finish the quiz. Okay, and so it says on there exactly how much time that you'll have as well. Are there any questions about the quiz or how that'll work? Okay, so the other part about the quiz is you do have until we meet again next Tuesday to take the quiz. So as long as you start it between now and then, or finish it between now and then, it's totally fine. So you can do it whenever you do have that time between now and Tuesday. Then the exam is going to work similarly, where I'll open up the exam after class next Tuesday. So today I did want to just go over just some basics about like what some of the topics are if you want to take the weekend to do some studying for the exam.
Yeah, it's next week.
Okay.
But it's going to be open for a week.
And please, if you have questions, please ask as I'm going here. It helps a lot just to, it makes me feel like I'm not talking just to a webcam all the time. So, where we left off, again, I'm going to go over, just kind of wrap up where we left off last time, and then talk about the exam, and then give you hints and kind of go over how to finish up the interpreter. So hopefully people have gotten pretty far with homework 6, and I really hope that just like I do every time I do it, there's this feeling that you get when you get it working, and it's actually like you can write code in a totally made up language or in MyPL, and your interpreter is now doing what looks like it should be doing. I would really encourage you, especially after homework 7, just take a little bit of time and appreciate what you have done, because it's pretty darn cool, I think. I don't know if anyone else had that feeling. Even just getting it to like print hello
I'm not
world
playing
or whatever,
God, I am God.
That should feel good. And you should make sure you take enough time to just kind of enjoy that. Okay. So moving on, I'm just gonna briefly talk about those features of Haskell. So last time we were talking about the major features of Haskell, and what I had said was it's not any one specific feature that makes Haskell unique.
I mean, they can hear me,
it's the combination of features that makes Haskell kind of a special language. So the first one, which is where we got last time, is that it's a purely functional language. And what that means is, in particular, is that you only have this notion of pure functions. Okay, so every function in Haskell is treated like a mathematical function. So for any given input, it only has one output. And the other way some people talk about this, or some of the ramifications of this, is that functions don't have side effects. They're side effect free. And that gives you kind of some interesting features that can be exploited for optimization. So one of the ways, or the two ways that Haskell does this or accomplishes this, is really what makes it different than any other programming language and takes a little bit of time to get used to or to wrap your head around. So the first is this notion that there's really no variables in Haskell. It's like all you have really are a bunch of constants. And then in addition to that, so right away, that's just very different. And then in addition to that, or as a ramification of that, in a function, you're never like modifying something, you're always creating something new. And it turns out, even like with a linked list structure or a tree-like structure, it feels very inefficient because you're always creating something new. But internally, Haskell actually has a mechanism for making this super efficient. And part of it is because of immutability. So for example, if I have a linked list and I add an element to a linked list, add a node to a linked list, what Haskell can do is it can kind of use the old list still and then kind of keep track of what new things have been added as almost like a diff or something like that, or like it just keeps track of the differences. And so it can basically, you can share existing structure. So even though it looks really inefficient, under the hood it's actually can be made quite efficient. Okay, so moving on, another kind of feature, and many languages have this, is Haskell is statically typed. And what that means is that that it is type checked, okay, at compile time. So just like with MyPL, we have a compile or a type checking step, and a little bit like what we're doing in MyPL is that it looks like oftentimes you rarely specify any types in Haskell, and Haskell itself is going to do type inference. It's going to figure out what the types are. So sometimes in kind of functional programming land, this is called unobtrusive. So basically you have like variables or whatever that are that you don't specify types for, but Haskell can figure out what the types are. This isn't really that hard to do for things like variables, and we kind of found this out, I would say, in MyPL, where we can figure out the types implicitly. However, it's a lot harder for functions, and Haskell can do it for functions. And so this is something that's quite unique. You never have to really specify what the type is of a function. So what types it takes as parameters and what it returns, what a function returns. The system figures it out based on the definition of the function. Okay. We'll see this as we go, but this is it's static typing like a lot of languages have, Java, C++, MyPL, but it goes further than most languages in terms of its ability to infer types, such that really you never have to give a type at all. It can figure out all the types that it in your program. So the third kind of feature is that Haskell employs strong typing. So basically what that means, and there's different gradations of this, but what it means in Haskell is that with its typing system is that Haskell can actually guarantee that your program is not going to have any errors with respect to types. And one of the ways that it is able to do this is it does place some limits on how you can convert from one type, a value of one type to another type. Other languages like Java, C++ are also often called strongly typed, but there still are a number of cases where you can write a program that will have at runtime an error with respect to types. And actually, Java, for example, now tries to help with that in some sense, where it gives these warnings. So when we're doing conversions, when we're casting, if we don't check the type, and in some cases with generics you can't, it'll give you actually a warning telling you that this could result in an error as your program's running. So in Haskell, you're never going to get that kind of a warning because it can guarantee that there's not going to be type errors.
So
Yes.
Haskell doesn't have type coercion at all, right? Like there's no casting or anything.
It kind of does. Yes, it does,
That's an
but
answer.
there's some limits with respect to it. And we'll see this as we go, kind of how that works a little bit. So it's kind of a weaker form of coercion. Sometimes it's implicit, so that would be coercion, and then sometimes it has to be explicit. So that'd be like casting. But there, again, there's some limits and some constraints on how that works. Okay, so another feature of Haskell is that functions are what are called first class. I'll use the highlighter here. First class. Excuse me. So when something is first class, that really means that it can be used just like any kind of other construct in the language, or like a value in the language. When something is said to be first class, it can be treated like a value. So when we say functions are first class objects, what that means is that a function can actually be used just like a value. So you can pass a function into another function. You can then, like in the body of the function, call the function that you passed in as a parameter or as an argument. You can also return functions from other functions. You can, as within the body of a function, you can create a new function and maybe like return that, for example. You can have a data structure, like a list, and you can store functions in the list, and so on. And so it used to be that Haskell was a little bit, or some of the functional programming languages were unique with respect to this. This has actually changed over time. So some of these things you can do in Python, for example, now, or you've been able to. Java now supports a lot of features where functions can be used as first-class objects. You can pass functions around. You can kind of call them on the fly. You can create functions and call them on the fly. C++ has more and more features with respect to that. But I would say that there's a couple kind of interesting parts to Haskell with respect to this. So one, it's been doing this for a lot longer than the more mainstream languages. And two, you still get all the benefits of type checking. So, and then I guess the third thing about Haskell is it's this notion that functions are first-class objects is almost built into the language itself. So you end up using this a lot more than you would in other languages. It's more like part of the convention of using the language. And we'll talk about that more later. We'll talk about some of the support for what are called higher order functions, which is just a function that takes a function as an argument, and kind of how that's used and some of the benefits of that in Haskell later. Whoops. Okay, so the fifth kind of interesting feature that is hard to wrap your head around sometimes is this notion of lazy evaluation. So Haskell supports what's called lazy evaluation, which is different than strict evaluation. So pretty much every language that I'm aware of today, maybe other than kind of like logic programming, which doesn't really, it has something a little bit similar to this. I think Haskell is very unique with respect to this feature, although there have been languages in the past that have used lazy evaluation. So the basic idea of lazy evaluation is if you have a computation, you never execute that computation until you actually need to use the result for something. So for example, if I call a function and I don't do anything with the output, the function doesn't actually get executed. If I want to print the result of the function, it's not until I want to print the result that the function actually gets evaluated.
How does that affect like the memoization? Like, does it doesn't it store like the result and then save it for later in case you call it again?
Right. So there are some cases where you do, in order to carry out the function, you're going to need to do some computation. You're going to have to evaluate something. And so anytime you do that evaluation, that's going to kick in the memoization. Or it's up to the compiler whether or not it's using memoization or not. So it really doesn't impact it, because it can still, when evaluation does happen, it can keep track of it. It's just not eager. It doesn't eagerly do the evaluation. It waits until it actually needs to have a result until it does the actual evaluation. So there are some advantages of this, and we'll see some of this later. But one is you don't really need the compiler so much to figure out what computations aren't needed. If it's never, the computation results never used, then it won't do it anyway. So there's some potential performance gains that can happen. You're not relying on the compiler to figure this stuff out. The other kind of interesting thing is, so for some algorithms, so for example, for quicksort in particular, you can, so quicksort, people probably remember maybe from 223, that quicksort is a recursive algorithm for sorting a list. And so the way quicksort works is you basically, one call of quicksort, all it does is it splits the list up into two smaller lists, okay, two separate lists, and then calls quicksort on that again. And it just kind of keeps doing that until everything's sorted at the end. And so with lazy evaluation, you can call quicksort, but if you're not going to do anything with the result, actually nothing happens. But you can say, okay, I'm calling quicksort. I would like to know what the first element is in the sorted list that quicksort returns. And this will actually trigger a partial evaluation of quicksort. It'll split only enough to tell you what that very first element is. So it's like a left deep kind of traversal of the tree that gets generated from the quicksort recursive calls. Okay, and then you can say, well, great, I see what the first value is, give me the second, and it'll actually then kind of only call enough to give you the second thing. It's a little bit like how we implemented next token in our Lexer. We say, we don't just get all the tokens in one big list. We say, give me the next one, give me the next one, give me the next one. So lazy evaluation is great for that kind of task. The other thing that's really cool about lazy evaluation is that you can build an infinite data structure. So you can have like an infinite list. And you can pass those infinite lists around. Whereas if you did eager evaluation or strict evaluation, if I tried to pass an infinite data structure into a function, it's going to evaluate that infinite data structure before it gets passed into the function. So for example, if a non-infinite example would be if I call a function over an expression like 3 plus 4. In order to call the function in strict or eager evaluation, you have to evaluate 3 plus 4 first, get the value 7, and then pass that into the function. With lazy evaluation, you don't have to do the evaluation first, you just pass in the expression into the function. So the same thing is true with an infinite data structure. I can pass that into a function, and then but I don't have to evaluate it before I pass it in. So this is not possible to do in like C, C++, Java, because these use eager evaluation.
Huh?
So cases when you'd want to do that are, for example,
Tim.
If you're representing, if you have a lot of data that you're using in a program or something like that, this notion of lazy evaluation and infinite data structures very closely mimics what we think of as like an iterator or a stream, where we're just asking for the next thing. Give me the next one, give me the next one, give me the next one. So that's one place where lazy evaluation kind of comes into play. Because lazy evaluation is really built into the language, it makes creating things like iterators or streams very simple to do. And using those to do computations. And then another kind of benefit is you can build up more complicated control-like structures in the language itself. And you can do things that you can't do in other languages. So for example, now I wish I could use my pen, but I can't. We're looking here. Let's say I wanted to define a function, and I'll call it if, whoops, this is my finger, if then else. And if then else takes 3 parameters, right? It takes the first parameter would be the conditional on the if. The second parameter would be the so the second parameter here would be the body of the then, and then the third parameter would be the body of the else. So in a normal programming language, when I called if then else, all 3 of these things get evaluated in the very beginning, right? They would all have to be evaluated in order for me to execute the function. Whereas that is exactly not what we want to do when we have if then else. We want to check the condition, and if the condition is true, then we want to do this one. If the condition is false, then we want to do the third argument. And so lazy evaluation actually lets you do these kinds of structures or these kinds of function calls where all I'm really passing in is the code itself. It doesn't get executed until I need to execute it, which would be based on whatever the condition is. So one of the ramifications of this is in Haskell, there really aren't very many built-in constructs for control flow, because you can actually just write them as special purpose functions if you needed to, including things like for loops or while loops or anything like that. And there's other kind of interesting uses for this kind of thing. So that's just in a nutshell what lazy evaluation is, which is pretty cool. And then the last thing is, and this was kind of mentioned a little bit last time, is that Haskell is expression oriented. And what this means is that every statement that you find in Haskell always is an expression. So there's really no statements, you only have expressions. And when I say expression, what we mean is that statement evaluates to a value. So in other words, everything returns or evaluates down to some value. And this is even true for if statements. And we'll see some examples of this later when we start talking more about the syntax and the details of the language. So it's just something to keep in mind, that Haskell really gets its roots from lambda calculus, which is the same way. Everything kind of evaluates to a value at some point. Okay, so before I go on, I'm going to move away from this. Those are the main kind of 6 features of Haskell. I'm going to stop there. And then that's kind of like a teaser for when we do start talking about Haskell on Tuesday. But are there any questions before I move on?
So about expression orientedness.
Yes.
So everything evaluates to an expression, but because functions are first class objects or whatever, a statement could evaluate to a function, right?
Right, and then every function has to return a value.
Okay.
So, or a function is a value. Functions are first class, so a function in and of itself is a value. if I call the function, it's going to return a value. Every function does, no matter what.
Yeah.
Like we said last time, there's no void functions, for example.
Besides functions, what are other examples of statements in Haskell for expression oriented?
Everything is a function. Everything is a function. At the end of the day, everything is a function.
I have a question about how you mentioned the functions cannot be void.
Yes.
Are there situations where that is problematic? And if so, how is that mitigated when you're using the Haskell?
Haskell. So I'm gonna hold off on that. And I'll touch on that actually after we kind of go through. So it'll make a lot more sense, I think, once we kind of get through what Haskell is and the syntax and stuff like that. So I think
Sounds
that's
good.
a great question, but I'm gonna hold off on that.
So one question about infinite data structures. So when you say that, the impression I get is it's not like necessarily infinite data structures, but more really, really large data structures. You have a better, or you can handle them better. Is that more accurate?
Yeah, but you can also create infinite structures. So for example, I could create a linked list that holds all possible ints. But the thing about it is there's certain things I can't do with that. So I can't say like print yourself. I can't print that out. But I can say, give me the first value, give me the second value, give me the 100th value, give me the millionth value, give me the billionth value, and so on.
Okay, so it's sort of like you make theoretical infinite data structures and then you actually evaluate it.
Right.
Okay.
A little bit, yeah. I mean, because you can't realize it, right? Like you can't instantiate it.
So if you're dealing with something like the example you gave where you have a data structure that contains all possible ints, is that isn't saved in memory? That's just sort of evaluated for the specific.
No, yeah. It can't be saved, but it can be slowly calculated.
Okay.
It can't be saved. Yeah. You can still use it for doing stuff, but you can't save it. Okay, so we'll good. I'm glad. These are great questions. I think people are starting to think about this, and we'll cover all of this stuff over the next few weeks. So as we dive deeper into Haskell. All right, so I'm going to talk about the exam real quick. So most of this I think I've already said. Excuse me. So the basics of the exam are that it's open book, open notes. So that's kind of different, and there's some complexities there. Again, like the other exam, the first exam we had, it's worth 10% of your final grade. So the second one and the third one will be the same. I think my goal right now is I'm going to make it just a 1 hour fixed time exam. And then again, like the quiz, you'll have to do that in one sitting.
Fuck, dude.
And then it'll be like the quiz administered through Blackboard. Okay. So in terms of the topics, it's pretty much what we've covered since the last exam. So this includes AST creation. So we had a quiz that was right before spring break that had some questions related to that. So there might be something like that on the exam. And hopefully everyone got back. Everyone that took that got that back via email. I had those scanned and emailed, so hopefully people received that. So then some things we talked about, we talked a little bit more about grammars, and in particular associativity and precedence issues that can occur with a grammar and with parsing, and then some ways to deal with those. So I can imagine there might be a question or a small question related to that, sort of like how would you bring out the associativity in this grammar or something like that. We talked about scopes, environments, and symbol tables, and we did that mainly as a constructively through MyPL. So where we had to deal with these things in MyPL. So again, there's been a few questions like on quizzes about this. Even the quiz that's out now or after class, that'll have a little bit of this on there as well. We've run up against, quiz 4, not 5. Cool, thank you, Tristan. So sorry, this was quiz 5. What was quiz? This was quiz 4. What was quiz 5? I can't remember now. I have to look. So then we've run up. What's that?
Quiz 5 was scoping.
Scoping. Okay. Okay, cool. And that was the extra credit quiz, I think, quiz 5. Okay, so then we talked about static and dynamic scoping. So that would have been a question on quiz 5. And so there'll probably be something related to that, maybe similar to quiz 5. We talked about, obviously we talked about static analysis and type checking. So really type checking is just one part of static analysis. So with respect to this, so I want you to be able to understand the type checking rules. Also kind of all of the things that are involved in type checking. And I think we covered a lot of that with the MyPL and implementation. And then probably some simple examples. So I might say, implement some code, write some code or pseudocode that does the type checking for this grammar or for this part of an AST or whatever. Okay, and then similarly for interpretation. So that's homework 6 and homework 7. So I expect that you now have a good sense of what's going on in an interpreter, or at least in a pure AST interpreter. And then probably the way I would test that would be through some maybe simple kind of coding parts. And then lambda calculus. So that's kind of the newest topic. So quiz 6 has some lambda calculus on it. So some stuff kind of like that. All right. But again, I'm going to try to keep it a little bit shorter, and so there'll probably be fewer parts to questions, but it'll be kind of focused and probably a bit harder than the other exams just because it's open book, open note. But I'm trying to make it doable, and I don't want it to take you forever, so I'm going to try to keep it relatively short. Are there any questions?
So is the whole exam going to be like short answer and there's no like multiple choice or anything?
That's right. Yeah, I hate multiple choice. And you should too. No, everybody should hate multiple choice. Everyone should hate it. Okay, anyway, yes.
Strong.
And then so following up with that, like is the lambda calculus like kind of how you said last class where you just have to determine like what the output would be? Are we supposed to like write out the steps on the computer or just kind of like give what the output?
Yes. And quiz 6, there's an example of that. So I kind of tell you how to write it out. So you're not using the lambda sign. Basically,
are we going to get quiz 6 back before the test?
Well, I hope so, but it kind of depends on when you start the exam, right? So if you start the exam right after class on Tuesday, no, I'm not going to be able to get it back. Yeah. Okay. But I will try to get it back, or at least I'll try to give you kind of the answers to what the quiz was.
Or even just like a blank quiz.
What's that?
Or even just like if you could just put out a blank quiz if you can't get them back on time, just so we could see what the questions would look like.
That's actually the way I set it up in Blackboard. I give you the blank quiz.
Okay.
So just save that.
Okay.
Yeah. So yeah. I'll try to I'll see how it goes with the grading and how long that takes. And if it's obvious I'm not going to get it done, then I'll make sure to provide in some form the answers.
Last question. So once you
Yep.
give us the exam, do we have, like you said, the whole week to do it, like until the next Tuesday, or what's the time zone for that?
Yes, but however, well, you don't have the whole week to do it. You have the whole week to sit down and carve out 60 minutes to take the exam. But you have to do it all in one sitting. So once you start the exam, you'll only have that 60 minutes. You can't pause it and come back to it. So for example, if you'd like to do it over the weekend, you just hold off until you're going to sit down for an hour and do the exam. And then, so when you're ready to do it, you would start it, and then you'd have exactly 60 minutes to finish it. Does that make sense?
Yes, thank you.
The same is true for the quiz. So the goal of the quiz is to simulate that a little bit. So you get practice doing that before. Okay, so I'm going to move forward. The goal for the rest of the time, so the half an hour we have left or less, is I want to go through, basically give you hints, and I'm just going to walk through the lecture notes that I'm providing for how to do homework 7.
And I'm paying
so
attention.
For homework 7,
hello.
the goal is to wrap up the interpreter. And what's left to do after homework 6 is the basically user-defined types, user-defined functions, and then as part of that, return statements. So those 3 things are all that's left. And I think it's actually, if you understand kind of what's going on, it's much easier than homework 6. But you do have to understand kind of how it's supposed to work, or how it should work. So it took me a lot less time to do homework 7 than it did homework 6, for example. Of course, I've done this now like a ton of times, so I kind of know what's going on, hopefully. So one of the things for homework 7 is we're going to use these additional kind of features of the symbol table that we haven't had to use up until this point. And in particular, we need to use, what we need to be able to do is jump between environments on the stack. And in particular, we need to be able to insert a new environment kind of in the middle of the stack, which is the symbol table is a stack of environments. Okay, so we need to be able to insert environments like within existing environments and then be able to remove them. And the reason that we need to do this, for example, is for functions. So when we call a function, we basically, because we're using static scoping, we need to go back to the environment where the function was defined, and then we need to insert a new environment to run the function in at that point. So that function only has available to it the function that or the environment that it was defined in. Similarly, so you have to get this right in order to also do recursion. So when a function calls itself, it needs to go back to where that function was actually defined. So you're going to end up kind of adding and adding and adding environments, and then when the function is done, you're popping those environments back off. Okay, so the two additional functions that you're going to need in the symbol table for that is to get the environment ID. So what this does is whatever environment you're currently in, if you call get environment ID on the symbol table, it's going to return an identifier that is a handle to that environment. And then if I want to jump to a different environment, you can call the set environment ID function. You pass in the environment identifier you want to jump to, and then all of a sudden you're sort of back into that environment. I'm going to show some examples of how this works. Okay, so I don't reveal too much. I'm going to do it this way, although it looks funny. So here, in the example, we're basically just creating one environment, and we're calling it E1. And so the first step is to create E1, we're going to push the environment. Now we're sitting in the E1's environment. So if you think about the stack, so on this side, if you think about the stack, sorry, let's say there's just this one environment in the stack, or there could be more stuff down here. We're just not worrying about it at this point. So the top of the stack, though, at this point is this E1 environment. Okay, and so over here, once we push the environment, we then get the identifier, okay, for E1, whatever that is. We store that. Then we're going to add the ID X, and we set X's value to 0. So now in E1, X has the value 0. Okay, everybody good with this? All right, so now we're going to push a new environment. We're going to push a new environment, and this time we're calling this E2. So we're pushing a new environment. So that pushes this environment on top of E1. And now if we think about it like a stack, we're sitting now at the top of the stack.
What if you push 2 in a row and didn't assign
So
the
then
one in the middle? Can you still
in
get to
E2,
it?
we also add X, and we set X's value to 2.
I don't know. You
And
might
now,
address
with
that.
respect to E2, this is a different X than the
Well,
one
then
in
he'll love that you're
E1.
giving him a segue.
And X here also has a different value. Okay.
Well, I mean, I guess it would make sense.
So then what we're gonna do is push a new environment between E1 and E2. So we're using these new features now to insert in between environments. Okay, so the first thing that we do is we go back to the environment for E1. So calling symbol table.set environment ID and passing in E1's environment identifier basically kind of sits us back here as if this is the top of the stack. Then we push a new environment, so that pushes this E3 environment, the third environment, above E1 and makes this the top of E3 now the top of the stack. So E2 is still there, it's just beyond what's now considered the top of the stack. Okay, and then in E3, so we get the environment ID for 3, we add X equals 3 to E3's environment. So now we've got 3 versions of X floating around. Okay, so if I were now to call get info on X, because my current environment is E3 and X is in E3, this is going to return the value 3 in this case. Are there any questions about that?
So
Nothing?
push environment doesn't push to the top of the stack, but just above whatever the current environment is.
Right. So here, because we basically, you can think of set environment ID as moving the top without getting rid of anything else. And so when we said set environment ID to E1, what we're really doing is we basically assigned E1 to become the new top. And so then when we pushed, but without getting rid of E2. So then when we pushed it, we just did the normal thing, right? Like we pushed from the top, and now this became the top, E3 became the top, and E2 is still there. So for example, if I wanted to go back to E2 to being the top, I would say symbol table.set environment ID to E2, and now all of a sudden E2 would be the top. Does that make sense?
Yeah. And if we called pop, would it pop E3 or E2?
That is a great question. So, so here's an example of that. So when we left this part, we still had E3 as the top of the stack. And so now if I call pop, it's going to pop from the top of the stack, which means it gets rid of E3. And now E1 is, and then E1 becomes the new top of the stack. And again, to get back to E2, I'd have to set the environment. To get E2 to be the top again, I'd have to set the environment ID back to E2.
Oh, this shit's easy.
So basically, we're going to use this as a mechanism. When we call a function, for example, we're going to save the current environment ID that we're calling the function from. Then we're going to remember what the function definitions environment ID is. We're going to jump to that and make that the top of the stack. And then we're going to push a new environment at that point in order to execute the function. And when we're done executing the function, we're going to pop that off the stack. And then we're going to jump back to the calling environment. So that's the idea. Okay. So sorry, there's kind of a lot of stuff here, but we'll go through it one at a time. So it turns out basically, so I'm going to talk about user-defined types first. They're a little bit easier actually than functions with respect to this. So, but I just want to say it's somewhat of a similar process for when we create a new instance of a user-defined type. We need to jump back to where the environment where the type was defined, and then we create a new environment that we use to build the object of the type in, and then we exit. We basically remember that object, we pop that environment we created, and we jump back to the environment where we're calling, creating the object. So it's very similar in that sense. So what's listed here are just some details about how to represent, in Java, how to represent the idea of an object of a user-defined type, and then kind of how to deal with that. So the first thing is that, whoop, see if I can, there we go, is that just in terms of terminology, when we call new on a user-defined type, what's created is an object. Okay, and we need to store that object somehow. And the way we're going to do that is we're going to store it using a hash map. And so the hash map basically just is a list of attribute value pairs, where the attributes are the attributes in the user-defined type, and then the values are the expressions that initialize those attributes. Okay. In addition, we're going to calculate for every object that we create, we're going to keep track of an object identifier, and I'm calling that an OID. And I'll actually give you the code to do that. But basically, you just pass in this map object, and it's going to return to you some big number. And you just want to store that number to represent the object ID. So really, you can think of this like a reference to that object value. It's like a reference to the object value. So then, if I were to say something like var, I hate to even try to write this. Maybe I can just type this. Yes. Okay, well, I can't really see. There we go. Var x equals new t. Sorry for the sound. Okay.
Yeah.
So if I were to write this statement, sorry for the capitalization too, var x gets assigned a new t. What happens is this new t is going to do two things. So first, it's going to create, the first thing it's going to do is create this object. Okay, and then the second thing it's going to do is it's going to calculate or get an object ID based on that object. That object ID is what actually gets stored in X. So X is going to hold an object ID. Really, what's happening is that it's holding the OID as a reference to the object value. So the OID is what gets stored, what actually gets stored in the variables. So what this means is if I do something like if x equals y, where x and y are both variables that are holding, that are referencing objects of type t, all I need to do this comparison, because I know it type checks fine, because the type checker works, all I really am doing is comparing OIDs. Or do they point to the same exact object? Do they have the same OID? So actually this approach makes these kinds of comparisons very, very simple. X equal y or x not equal y. In addition, it means that when we call a function and we pass in, for example, x, all we're actually passing in is a reference to x. So for our user-defined types, we're always passing by reference, okay, like in Java. For non-user-defined types, we're actually passing by value. So we pass the value in for the parameter. And really, we're doing the same thing here. We're passing by value. It's just that x holds as a value the object ID. So this is exactly the way that Java works. Okay.
Just to clarify, you're saying that multiple objects or multiple instances of a type can have the same OID then?
No, they'll have different OIDs.
Then how does the comparison, like that example you gave, work then?
So if I somewhere else, like later in my program, if I said something like set x equal to t, let's say, and then later on I want to say maybe there's a conditional that x gets set to y if some condition holds, and then later I'm going to check is x equal to y or are these different. So at that point I'm just comparing the OIDs. Are they really this kind of referring to the same OID?
Okay, gotcha. Thank you.
Okay, so then the last thing we need to do is we need to keep track, we need to remember the object values. And so the way we do that is we're going to create a heap within the interpreter, and it stores the object values. So it's going to store the hash maps. going to store these maps that represent the actual object. And the heap itself is going to be a map, a hash map. And the hash map has the structure where basically the key is the OID, and then what gets stored is the actual value of the object. Okay, so one of the things that this means is that when you have a statement like this, var x equals new t, that object gets put into this global hash structure, which is just stores the object values, maps them to object ID. But when we lose, when x goes out of scope, that object value stays in the heap. Okay, so we have like the worst of all worlds in MyPL, where well, it's good that objects can live beyond their current environment. However, we have no garbage collection supported, and we also don't have a delete mechanism. And so that means once you create an object, it lives for the rest of the program's execution. So every time you do this in MyPL, you're actually creating a memory leak.
Great.
You literally have no way to delete it. Again, so if we were doing the projects, this would be a very natural extension to MyPL, would be to implement either garbage collection or to implement some mechanism to do a deletion. Okay. And then finally, the last piece is that, and actually I'm not even really going to talk about it, is that it turns out that the rest of the support for user-defined types is really these path expressions. And the path expressions, what you're doing is so like if I say x.a, for example, all I'm really doing is I'm taking x, which is an object ID, I'm, quote, dereferencing it, which means that I take its value, which is an OID, I look it up in the heap, I get the actual object value, and then I pull out the attribute and its kind of reference, and then I keep going that way. So it turns out that it's almost identical to doing the type checking. So dealing with the L value and R value path expressions is almost identical to what you would do in type checking. The only difference is you were calling them OIDs and a heap. Okay. All right. So then this just kind of walks through some of the steps or how this might work. So I'll go through this fairly quickly. This is something you probably want to go back and look at. You want to understand the approach, and then you want to go back and look at this just to make sure, like, this is kind of giving you some hints as to how to actually encode this stuff in your interpreter. So the first thing is we're visiting a user-defined type declaration, okay? And so what we need to do, so basically this is the definition. This is a type statement. So we need to record the definition of the type. We need to keep track of that. We need to remember that. And then we also need to keep track of the environment where the type was made, so that when we create the object, we can go back to that environment and we can go back to that definition and we can create an object from it. And so, the way that we're going to do that is or one way to do that is we basically create a small list that contains just two elements. So it's going to contain the environment ID of the type declaration. And then we're going to keep track of the type decl statement node itself. And then in the symbol table, we take the name of the type, which is, let's say, T, and then we set its info to this list. Okay, so when we go back and we say something like new T, we're going to look up T in the symbol table is going to give us back this object, and so then we'll have the environment ID and we'll have the type decal statement. Okay, so that's kind of described here. So the first step when we see new is we get back the type information. Okay, and then we're going to want to grab our current environment where new is being called. And then we basically do this time jump. So we jump back to that environment that T was defined in. Okay, and then we're going to create a new object as a hash map that's going to represent the object value. We then also generate the OID from that object. And then we go through the type decal statement and we fill in the object. Okay, and then when we're done, once we've filled in the object, we pop the environment and then we jump back to our current environment. And then once we've done all that, now we've built up the object. So the last step is we want to add the object ID, this connection between the object ID and the object back into the heap. And so that's what we do here. And the heap, you need to declare as a new instance variable or a new member of the interpreter class. And so this ugly thing is how you would define that. So basically we're saying that a heap is mapping from an integer to another structure, which is the representation of an object. Okay. Any questions about this? It's kind of a lot of stuff, but really this is more of a guide as you try to implement or finish up the homework assignment. Okay, and then the last thing is implementing functions and function calls. So we basically already walked through this. So again, it's very similar to a large degree to doing the types. So when we get to a function declaration or function definition, a fun statement, then what we're going to do is the same thing we did with the types, is we're going to record the AST node in the symbol table and then also the current environment. And then there's all these steps for actually doing the function call. And actually, we already talked about all of these already today. So I'll just go through it super fast. So when you're going to do a function call, you first want to go back and get the function information. So that's the environment ID and the AST node for the function. Then you store the current environment. Then for the function call, you need to go through and evaluate all the argument values. Okay, and then you need to keep track of those. That's what's going to be passed into the function itself. Then you go to the function declaration, that environment, you create a new environment, that's where the function is going to run. Then you basically set the parameters of the function, those variables, to the argument values that you remembered back up in step 3. And then basically you just, you visit the function statement list. Okay, and there's one caveat here, which is how to deal with return statements. So I'll talk about that in just a half a sec. Then you basically, once you're done with that, you remove that new environment you created and you jump back to the caller's environment, the one that you started the call from. Okay. And then the last bit is how do we deal with return statements? So it turns out return statements are a big problem, and there isn't really a very good way to handle them using the visitor pattern. Okay, and the reason for this is when you hit a return statement, you're basically just abruptly leaving the visiting of the statement list, right? So you just kind of violently exit that. And there isn't a great way to do that. So what we're going to do in the way I'm suggesting you implement this is to just use exceptions. And basically, when you hit a return statement, when you visit a return statement, you're going to throw an exception. And the exception you're going to throw is just another MyPL exception. But we added some additional functions to deal with return statements. So there's a different constructor that takes the value that's being returned, and then you can check for any particular MyPL exception whether or not that was a return exception or not. If it's a return exception, then you can get back that value. So it's just basically holding the return value. Okay, so this is what you do from within the return statement. Once you get the return value, you basically, you just throw a new MyPL exception, but it's a special one, which just is holding a return value. Okay, and then basically you have to have a way to catch this exception when you're executing the function. When you're executing that statement list, it can throw an exception, which could be one of these return exception variants. And so if that happens, then basically your job is to kind of handle that return exception. So you just need to check, is it a return exception? If it is, then you set current value to the return value. If it isn't, then you just basically pass on the exception, because that means it was an error. And then finally, there's a few small changes that need to be made to the run function to handle return types. So this is kind of a hint, and to some degree, this tells you how to change the run function, but it's also, this part is really a hint of how to handle this part at the start. And that's all. That's all I have. And we're actually over time. So my suggestion is to get started on this, and then, but you do have a good amount of time to finish it. And so I think it's important that you look through the notes and you try to wrap your head around it and figure out what's going on, and then come on Tuesday with additional questions, also on next Thursday, and I can try to clarify any questions that people have. And we're over time now, so I apologize for that. And I'll stay around here for a few minutes. People can leave, but if you have questions, I'm more than happy to answer questions.
Yeah, I have a question that's like not super related to the implementation, but like
Alrighty.
the numbers, the ID numbers that you get for the environments and the object
Donovan,
IDs. Like,
can you fucking believe it?
How do you generate those?
How are those generated?
Yeah.
Well,
Believe what?
So that's a great question.
Prices are fucking $23.
So actually,
oh my god.
In Java, it's
all
a
my
little
turnips
bit
are gonna rot, and I'm gonna be out
tricky.
whatever
Where's the
100 times 500 is.
Oh no.
Oh no.
Let me find it here real quick.
I'm sorry. I spent around 50,000 on tulips too.
Oh, here it is.
It's
So
not turning out
this
very well.
line right here.
On tulips? Oh, those are different.
I meant radish, whatever it is.
All right.
There we go.
Yes, those.
So that basically.
Oh, well, just
this
like
is
the
a
real
trick.
world stock
okay,
market.
so
yeah.
Java
it's going to shit recently too.
actually does exactly this, pretty much the exact same thing as what we're trying to do. So when you create a new object in Java, it stores that in the heap. And so it needs to have a way to kind of remember where that is in the heap. And Java is kind of like a hybrid interpreted compiled language. And so it itself has to generate these unique IDs. So in something like C++ or C, it can rely on the fact that you can use the addresses, memory addresses in the actual heap space of the program to be the object identifiers, right? That's kind of how C works. But in Java, it's a little bit trickier. So effectively, so one way to do this is to just keep like a running tally of the objects that are created and use those as the identifiers, right? So you can kind of like generate your own